Hi folks, welcome. This is the second session for the BODG 1022 Building Structures Calculation Question Revision. Today we will work through some key concepts, calculations, and tutorial questions. Okay, let's begin today's session. First thing first, a little bit of introduction about myself. My name is Jesse. I am a graduating student in construction management and property. Previously, I have completed the course BODG 1022 Building Structures in term 3 last year. I have previously worked in the residential sector of the industry as an estimator and also a project coordinator. I will be your mentor for this subject this term. Let's begin. So, a little bit of recap on what have we covered last session. To solve calculation questions, you will need to firstly understand the key steps in solving every calculation question. First off, you need to understand the concepts that's involved with this question, as in which week's content is this, and you also need to gather data from the question, say what's the mass of the object, what's the maximum deflection, what's the bending moment, etc. Secondly, you'll need to find the proper formulas related to the question. After that, you will need to rearrange them and combine them so you can figure out what's the known and unknowns. Third, determine the knowns and unknowns, utilize and substitute the figures provided in the question using the equations that you have previously rearranged and combined. Lastly, simply do the math. Note that to be careful when you are converting the units, they can be tricky sometimes. Moving on in today's session, we'll be mostly talking about calculation questions relating to loads, steel, and we'll also have some further elaboration on stress and strain. Moving on, the first concept I'll be covering today is the loads. There are three kinds of loads you need to familiarize yourself with for this subject. They are the dead load, the live load, and the wind load. Firstly, we have the dead load. The dead load is a kind of permanent load that is imposed by the building components or the building structures. The reason why the dead load is permanent is in most cases there won't be any alteration to the building structure. Thus, the load imposed by the building structure or material used to construct the structure will not change. To calculate the dead load, simply multiply the volume of the material by the material's unit weight. Secondly, we have the live load. The live load is a temporary load imposed by unfixed items such as people occupying the building or furniture and appliances. Similar to the dead load, the reason why the live load is temporary is because the people or furniture that's imposing this load can be easily replaced or removed. For the calculation of the live load, firstly, you need to determine the building's purpose, because for different purpose of building, there will be different kinds of people occupying it, and there will be different furniture that is needed for this purpose of the building. After which, you will need to find a appropriate uniformly distributed load in the table provided to you. Then you will calculate the live load by multiplying the slab area and the applicable uniformly distributed loads. Lastly, we have the wind load, which is obviously imposed by wind. However, please note that in different heights of the building, the wind load can be different due to the altitude and the speed of the wind. The reason why is that we need to take into account the effect of the wind load is because due to the increasing popularity of the lightweight material used in high-rise buildings and also in medium to low-rise buildings. For the calculation of wind loads, firstly, you need to determine the graphic project location. Then you need to choose the right terrain category and find the needed wind load pressure. As far as formula for calculating wind load concerned, you simply multiply the impact area of the wind load by the wind load pressure that you find in the table and graph. Lastly, I want to remind you some of the questions you meet may ask you to calculate the combined loads of a project. Therefore, you need to see all the applicable formula provided in the question that you might need to solve this question. Moving on, I'll walk through some of the load sample questions for you. First question, it says, in the graph attached below is a 220 mm thick, 6 meters long, and 4 meter wide reinforced concrete slab with 4% of steel reinforcement. Then the question asks you to calculate the dead load of the reinforced concrete slab. As we know from the previous slide, the dead load equals to the volume of the material used multiplied by the weight of the material. From the table attached below, we can see that the unit weight of concrete is 24 kilonewton per cubic meter, and for every percent of steel reinforcement, the unit weight adds 0.6 kilonewton per cubic meter. Therefore, for the concrete slab with 4% of steel reinforcement, as the question mentioned, the unit weight will be 26.4 kilonewton per cubic meter. Additionally, as the dimension of the slab is already provided, we can easily calculate the volume of the slab equals to 5.28 cubic meter. Lastly, simply calculate the volume by the unit weight of the material. We can get the conclusion that the dead load equals to 139.4 kilonewton for the concrete slab shown in the graph. Moving on, now we have a question that is based on the wind load calculation. In the question, it requires you to calculate the total wind pressure on wall AB and DC based on the internal and external pressure shown below. Assume that all the other internal and external pressure does not exist if they are not shown in the graph. If we take a look in the graph, we can see that for the wall AB, the external pressure and the internal pressure acts to the contrary directions. The external pressure is 12 kilopascal, while the internal pressure is 6 kilopascal. After the internal pressure and external pressure on wall AB offsets with each other, we can easily calculate that the wind pressure on wall AB affects at 6 kilopascal to the right side of the wall. As for wall DC, we can see in the graph that the external pressure and the internal pressure act to the same direction. Therefore, these two pressures will act combined with each other. Thus, the wind pressure on wall DC is 12 kilopascal to the right side. Moving on, we have the last question for wind load calculations. In the question shown is a multi-story building with a story height of 4 meters, a dimension B of 6 meters, and dimension L of 10 meters. Now the question requires us to calculate the wind action on level 3. In the graph shown, we can see that the wind pressure on level 3 is 3 kPa per square meter. Additionally, the dimension of the building is shown in the question. You can easily calculate the wind action on level 3 by multiplying the length and the story height, as well as the wind pressure on level 3 is 3 kPa. After we do the math, we can calculate the wind action on level 3 is 120 kilonewtons. The part B of the question asks us to calculate the total wind action on the entire building. As we know from the previous question that each level of the building have the same impacted area for the wind action. However, the wind pressure is different for each level. Therefore, we simply calculate the wind action of each level and combine them together. After we do the calculation, we can get the conclusion that the total wind action on the whole building is 420 kilonewtons. Moving on to the next part of our session today, steel structure. The calculation questions on steel structure will mainly be deflection-related calculations. For the calculation of deflections, we have two formulas. One formula is used when the load to the beam is distributed at a point of the beam. It's also known as point load. The other formula will be used when the load to the beam is evenly distributed or uniformly distributed. Moving on, I will now explain what the symbols in those formulas mean. First off, we have the symbol of maximum deflection, which is calculated by the length of the beam divided by 1000. The unit for this is in millimeters. Next up, the uppercase E is usually 200,000 milliPascals. This number is usually set or you will be provided in your question. The lowercase w is the uniformly distributed load to the beam. The lowercase p is the point distributed load. The uppercase I is the section area in question. The lowercase l, of course, is the length of the beam. Finally, when the question requires you to determine the universal beam section by finding the nearest figure to calculate answer in the one steels table. This table will be provided in your exam. Moving on, we now have a question says, a 12-meter simply supported beam is subjected to a 8 kN per meter download uniformly distributed load. The question then asks you to determine the lightest UB section so the maximum deflection does not exceed L divided by 1000. So the first step we need to do to solve the question is to gather data. Firstly, we know the UDL equals to 8 kN per meter, which equals to 8 Newton per millimeter. Then we can know the length of the beam is 12,000 millimeters. After which, as I mentioned in the previous slide, the uppercase E equals to 200,000 milliPascal. Additionally, the maximum deflection equals to L divided by 1000 equals to 12 millimeters. The second step of solving the calculation question is substitute all the data you have gathered in the previous step into the appropriate formula. After finishing substituting the figures you have gathered, you can see the only unknown figure is the section area of the beam. After we done the math, we can have the figure for the unknown section area. Since we now have the unknown, we can easily find the nearest section area in the one-steel table provided. In conclusion, the section area 610 UB125 will be the lightest UB section that the question requires you to determine, so that the beam does not exceed the maximum deflection. Moving on, what we have here now is another question for determination of the lightest UB section. However, for this question, the load to the beam is distributed at a point of this beam. Therefore, you will need to replace the formula of maximum deflection with a more appropriate formula for this scenario. All the other steps of solving this question will be identical to the previous question. I will recommend you to go through this question at your own spare time. The three steps will be firstly to gather data, secondly to use appropriate maximum deflection formula and rearrange them to identify the unknown section area of the subject. Lastly, simply find the nearest section in the one-steel table provided to you. Okay guys, now we're at the last section of our presentation today. Stress and strain due to bending. Calculation question based on stress and strain will normally ask you to determine the smallest UB section that the beam does not yield. Typically, there will be three key formulas to be combined and rearranged to solve this sort of a question. Firstly, we have the maximum moment, which equals to the uniformly distributed load to the beam multiply the square of the length of the beam divided by 8. Next up, we have the formula of yield stress, which equals to the moment multiply the y-coordinates of the beam shown in the graph below, divided by the section area. Lastly, we have the section modulus, which equals to the section area divided by the y-coordinates length. Moving on, what we have here now is the last question of our session today. The question asks, a 10-meter long simply supported beam has a uniformly distributed load of 18 kN per meter. From the one-steel table, find the smallest UB section so that the beam does not yield. The steel has yield strength of 220 MPa. Ignore the effect of the beam's self-weight. So as usual, the first step to solve a calculation question like this is to gather data from the question asked. From the question, we can see that the UDL is 18 kN per meter, the length of the beam is 10 meters, and the yield strength is 220 MPa. After we find this information, we are now to find formulas and rearrange them to the calculation and hence determine the smallest UB section so that the beam does not yield. After finishing gathering data from step 1, now we are to determine what are the formulas needed to solve this question. First off, we have the formula of calculating the maximum moment, which equals to the UDL multiply the square of the length of the beam divided by A. Therefore, we can calculate that the maximum moment equals to 225 kN. Since we already know that the yield strength equals to the maximum moment multiplied by the y section length divided by the section area, and also the section modulus equals to the section area divided by y coordinates distance. We can now proceed to step 3, rearranging and combining the formulas we have concluded. After rearranging and combining formulas, we can see that the section modulus equals to the maximum moment divided by the yield strength. The next step will be doing the math, after which we can draw the conclusion that the section modulus equals to 1023 multiplied by the 10 to the power of 3 cubic millimeters. The final step of solving this question is find the nearest z value in the UB tables of the one steel table provided. In conclusion, the smallest UB section after we find the nearest z value will be the 410 UB 59.7 section. And this UB section will be the smallest section that the beam does not yield. Hello guys, this is the last part of our presentation today. Firstly, I would like to remind you we are now another week closer to the final exam. I would advise you to start prepare for it before it's way too late. Secondly, whenever you are having any kind of difficulty understanding the concepts or working out the calculations, do not hesitate to seek help. Third, I would like to recommend you to practice your tutorial questions, especially the basic ones. These basic questions will ensure you to score at least half of the marks presented in the final exam. Also, the final exam questions will be having the similar difficulty to your tutorial questions. Therefore, it is a very good idea to practice your tutorial questions as much as you can. Lastly, I would just want to say that you are always welcome to reach out to me by the email address written here, or you can reach out to your lecturer, Dr. Samad, or any other tutors you have. Best luck to your final exam, guys. I'll see you around.